Let us see a few more properties related to ellipse. The tangents drawn at endpoints of latus rectum of an ellipse pass through the foot of corresponding directrix on the major axis. So what it means is, let us consider some ellipse, and these are the two foci. So clearly this is latus rectum and this is the major axis. Now, if we draw the tangents at the endpoints of the latus rectum, that is at L and L dash, because of the symmetry they both will pass through the same point, and this point happens to be the point through which even the directrix passes and cuts the major axis. Alright, so that is what is the meaning of this. If you consider the other latus rectum which is on the other focus, so there also the two tangents will pass through the same point, and that is again the foot of perpendicular of the second directrix which is present on that side. Right. Let us move on to the next property. The part of the tangent between the point of contact and the point where it meets the directrix subtends right angle at the corresponding focus. So suppose we have an ellipse, and let's consider the major axis here like this, and there is a directrix. This is the directrix. Now at some point on the ellipse, suppose we draw the tangent. Okay, it will cut at some point to the directrix, say M, and P is the point on the ellipse where we are drawing the tangent. So if we join the point with the focus, and also we join the point where the tangent is cutting the directrix with the focus, so these two will subtend a right angle at the focus. So this is the part, PM is the part of the tangent between these 2 points which subtends a right angle at the corresponding focus. So why they are saying corresponding is because, if you consider the second focus, the angle made by the same part will not be a right angle, okay, because we are considering the directrix on the right side. If you want to consider the angle subtended at S1 or S dash to be the right angle, then we'll have to consider the directrix on the left side and the tangent which also meets the left directrix. Going ahead to the next property. Now this is a reflective property, very interesting. It says that the normal at any point on the ellipse bisects the angle between the focal radii at that point. So suppose that we have an ellipse and 2 foci. Let us consider that at some point P we draw the normal. Okay, so by normal, you can consider first the tangent and then draw a line perpendicular to it, so that becomes a normal. Okay. Now if we join this point with the 2 foci S and S dash, the normal bisects the angle S dash PS. That's what is the meaning of this property. Okay, so for any point, the normal at that point will always bisect the angle between the focal radii. Okay. Now why this is called as the reflective property is because suppose you keep a light source at some focus, say S dash, and any ray that emanates from that and getting reflected internally from the wall of the ellipse, considering that ellipse is internally a concave mirror, then on reflection the reflected ray will always pass through the other focus. So no matter which point P we consider, the reflected ray will always pass through the focus. So that means if we consider some other ray, okay, on hitting the ellipse, when it reflects, it will always pass through the second focus. Okay. So that is what is the reflective property of the ellipse. Let us go ahead to the next one. Now this is again related to the normal. It says that no normal of an ellipse other than the major axis passes through the focus of the ellipse. So if we consider an ellipse, the normal drawn at the vertex, that is nothing but the major axis. Okay, and this normal passes through coincidentally both of the foci. But if we consider any other point, okay, so in that case the normal will never pass through the focus. in fact any of the foci, it will never pass through. That is what this property is saying. Let's move on. Area of the standard ellipse whose equation is given to us is pi AB. Okay, so basically when we know the equation of the standard ellipse, which we know that it is situated in this position where the center is at the origin. To find the area, basically what we do is we consider only the portion of the ellipse which is lying in the first quadrant, and we multiply that area by 4 so that we get the total area. The exact procedure of finding out this area will come in the topic of definite integration, which you will be definitely studying. So there we use the definite integrals to calculate the area under any curve. So when we use that process to find the area of the ellipse, it turns out to be pi AB. Okay. Where we know that A is the semi-major axis and B is the semi-minor axis. Now, as an interesting consequence of this is that if we consider A equal to B, that is if the semi-major axis and semi-minor axis are same, then what it means is the ellipse is nothing but a circle, correct? Because in that case A and B would have been the same. So we can very well call both of the lengths as A only. So in that case the area will get modified to pi into A, which is nothing but pi A square, and we are already aware that is correctly the area of the circle with radius A. Right? So this is the original formula, general formula, because ellipse is a general case, you can say, of the circle.